Hello everyone, welcome back to MTH1W. Today we are going to be looking at making sense of linear relationships. What is linear? Well, linear just means straight or in a line, and we're going to look at what that means and what that looks like in this lesson. So, first things first, our learning goals, like always. By the end of this lesson, we will be able to identify, compare, and describe the rate of change of linear graphs. We'll be able to represent linear relationships in different ways, such as tables, graphs, equations. We're going to look at one other way too today. And finally, we are going to be able to connect different representations of linear relationships to understand the meaning of slope, which is just the rate of change, and the y-intercept, which is the initial value. We are going to skip our success criteria and we will go over that at the end. But if you would like to take a look, those are the success criteria that are based on what our learning goals are. So if we take a look here, and as we talked about at the start, a linear relationship, or linear means straight or in a line. Well, it isn't as basic as that. It is when two variables form a straight line when they are graphed. Now, as you can see on the right here, it is a graph and it says where I am, and it's that really low point and where I want to be. And that is essentially why we have our success criteria. We are down at that low point right now, and we want to be able to do all of these various things that are based on our learning goals. So I will say that this graph, if you can't tell, is not a linear relationship. And why is it not a linear relationship? Well, we had already said that linear means straight or in a line. So if this was a linear relationship, it would go from the corner where the x-axis and the y-axis meet, and it would be straight up from here. If it was the same starting point here, it would be straight up and in a straight line. So we're going to get into a warm-up example. So you and two other friends are really excited. You're headed to the Taylor Swift concert in Toronto. You are taking a taxi to get to the concert. When you get in the taxi, the meter says $4. You're a little confused because I just got in. Why am I already being charged $4? Well, it's because a lot of taxi companies will charge a flat fee or an initial fee, hint, when you get in a taxi. As you drive away, the price starts to climb and climb and climb. And as you watch the odometer, you notice that each kilometer adds $2 to the meter. You know that it's also an 8-kilometer drive from your house to the venue. So the question for this is, do you think that we can predict the total fare without watching the meter the whole time? I do believe that we can, because we have a lot of important information here that we're going to use to do so. And that information is, the meter says $4 right at the start when you climb in. Next, we find out that, oh, each kilometer you travel, $2 more is added to the meter. You also know that it is an 8-kilometer drive to the venue. Let's take a look at what this might look like on a graph. So here we have our kilometers, or our x values, from 0 all the way to 6. We will probably add in an 8 here because we know it's 8 kilometers to the venue. And then we're going to find our cost. So our cost is what we're going to have to pay as we travel to the venue. And we noticed in the example that when we climbed in the cab, the flat fee, or the initial fee, was $4. So we're going to put a 4 right beside the 0 because we hadn't traveled anywhere yet, but they were already charging us $4. Next, we noticed that the odometer, for every kilometer we traveled, it added $2 onto that fee. So what I'm going to do is I'm going to take that 4 and I'm just going to add 2 to it and throw a 6 here. And then we get to 2 kilometers, and guess what? Yeah, we would be at $8. Then the next kilometer, 10, 12, 14, 16, and then finally $18. Okay? So this is one representation of a linear relationship. Pretty neat. It's in a table. We can make this representation of a linear relationship into a graph on this x and y axis here. And how I'm going to do it is I'm going to look at my x value, or the kilometers traveled, and I'm going to look at my y value, and I'm going to plot points based on the coordinates. So at 0 kilometers, we were at $4. So if I grab my pen here, and if I'm at 0 kilometers, that means that we are right on the y-axis, right? I will be at $4. So I'm going to plot a point right there. Next, at 1 kilometer, we're at $6. So here's the 1 kilometer, and we're all just above the 5 kilometer line. So I'm going to put it about here, and so on. So at 2 kilometers, we would be at $8. So a little closer to that 10. At 3 kilometers, we'd be right at 10. At 4 kilometers, we would be right at 12. Perfect. And then 5 would probably be right here. I'm just going to put a little 5, and we would be at 14. So I think you get the point of this. I can then take the straight line and graph all my points, and some of them aren't exactly on the straight line, but I'm human and I'm not perfect, and sometimes that happens, and we can tell that this relationship would be a straight line or a linear relationship. Now, going back to the example to answer the question, do you think that we can predict the total fare without watching the meter the whole time? Well, if we go back to Polypad here and take a look, we know it's 8 kilometers. We know that we started at 4, and every kilometer we travel, we added 2, so the total would be $18, which is right here. Next, what we're going to look at is the different ways we can represent a linear relationship. So we saw the graph. Let's look at shapes and patterning, or shapes and patterning and equations. So the first thing we're going to look at is equations. So equations. Linear relationships are in this form you see up here. And I know this is math class, but math includes letters, as we've talked about before. So a linear relationship is set up as y equals ax plus b. And your a value is the rate of change, and the b value is your starting or initial value. So in the example, tell me, what was your initial value? Well, it was 4, because when we got in the cab, there was $4 on the meter, and we hadn't even gone anywhere. Now, as they drove to the concert, it was adding $2 each time a kilometer passed, and that would be our rate of change. So, to show that, we will take a look at this. This is another way to represent that. How can we go from that graph or that problem and show it in patterns? Well, I will explain here. So at the very beginning when we got in the cab, holy smokes, that zoomed in a lot. When we got in the cab, let's see if I can, perfect. When we got in the cab, it was $4, and that's represented by these 4, which is our initial value. And then this was at 0 kilometers, right? I'm gonna put a big 0 here if I can. 0 kilometers. And then once 1 kilometer passed, it added $2. Once 2 kilometers passed, it added another $2, which made 4. And once the 3rd kilometer passed, and so on, you'll see 3, 4, 5, 6, 7. You'll see that the total fare kept adding up. And that's how you would represent this in patterns or in shapes. Now, let's think about this, for example. Now, this looks a little bit different, but we will I'll explain this here. So if we look at this graph and I turn these guys off for a sec, this shows the pattern that we were just looking at with the cab. So our initial value at 4, which goes on the y-axis right here, it moves and it climbs by 2 for each kilometer. The 1 would be, holy smokes, let's not use that. So for each kilometer we traveled, so this is 0.5, this is 1, the price of the cab climbs $2. So this would be our rise going up from 4 to 6, and our run would be like how we went 1 kilometer. Now, with different relationships, with problems that aren't this one, you'll see different things. So in this case, we start at 4, but the slope of our line or our rate of change is different. So if we look, we rise to 5 and we run to 1. So this rate of change would be just a 1. And in this one, our rate of change is even steeper. So as you'll see, if we take a look, we go over 1, and then it's all the way, the next point to line up with that is all the way 8 higher, which you'll see in the equation 8x. So that a value, as we talked about, is our rate of change, and our b value is where we start on that y-axis, right? So on the way home from the concert, you had to take another taxi home. And lucky for you, when you got outside, there were many lined up waiting for you to get in. And this is common outside of a concert where they know a lot of people will be coming out soon. They will congregate and line up, getting ready for you to come out of the concert so they can take you home. You think you're lucky, but normally when this happens, there's a lot more people than there is cabs available, even though it does look like there's a lot of cabs. So we'll get into why you weren't lucky. Because when you get in the taxi and look at the meter says $8 when you get in. Holy smokes, that's double the price that you started at. As you drive away each kilometer, the price increases $3 instead of 2 this time. You get really nervous that the total cost might actually be more than you and your friends have on you. So you calculate the total cost of the 8-kilometer journey home, like you did on the way there. So for this, please take some time to either create a graph of this relationship, a table of values, or a pattern, shape, series, or finally, if you want to, an equation that represents the total cost of the ride home. I will give you about 10 minutes to do so, and we'll come back and share what we did. Now, finally, in that last example, let's check if we were successful. In that last example, were we able to identify a graph, identify whether a graph shows a linear or nonlinear relationship? Well, yes, we were able to identify that it was linear because it was a straight line, right? Were we able to describe how a linear relationship increases or decreases at a constant rate? Yes, we were, because we saw that it increased by, I would have to go back to the example. Hold on one sec. If we go back here, it increased by $3 every kilometer that you drove. So at 1 kilometer, you increased $3. At 2 kilometers, you increased another 3. So we knew that it was a constant rate of change. Next, we were able to use a table of values to build a graph and write an equation for a linear pattern. So the hope was that you were able to at least do a graph to represent that last linear pattern. And finally, our last two were explain the slope and the y-intercept and what they mean in a real life situation, like when you get into a cab, and make predictions based on the pattern shown on the graph. Thank you so much for watching, and I hope you have a great day.